Let's have a few words about stability. Right now, we're in an equilibrium position. The weight's going down, the force of the stick acting up cancels out, and we are stable. How do we know we're stable? If I disturb the block from the equilibrium position, it returns to the equilibrium position. Why would it do that? Well, as I move it to the side, the weight coming from the center of mass misses the pivot, producing torque that brings it back in line. Now that's stable. Compare that to holding the block like this. If I let go, it starts to fall over, and it keeps going. It doesn't come back. The weight going down is being stopped by the stick pushing up. They cancel out, so it's in equilibrium. But the difference is that as soon as it moves a little to the side, the weight misses the pivot, producing torque that brings it away from that equilibrium position. So that's what makes this unstable. Let's see how that works with a meter stick. Well, here we have the meter stick, and it's balanced nicely. The center of mass is right under that pivot. Now notice I said under the pivot. If it's under the pivot, it can't produce any torque. If I disturb the meter stick from the equilibrium position, the center of mass moves to the side, producing torque, bringing it back under the pivot. That's a stable equilibrium. But what if I try to put the meter stick on top of the pivot and just get it to balance? Whoa, it's going over. That's unstable. So let's go back to the block. The weight of the block is going down. And let's put the pivot at the top. The pivot will pull up on the block, and we'll say this is in equilibrium. If I disturb it from the equilibrium, the center of mass is moved over slightly, and we can say that this weight misses the pivot by a slight distance. It produces a torque that will restore the block back to the equilibrium position. So we'll say this is a stable equilibrium. When you disturb the object from the equilibrium position, if it wants to return back, it's stable. Compare that to the situation where the pivot is at the bottom. The weight goes down, the pivot pushes up, and they'll cancel each other out. And as long as this is perfectly aligned, we would say it's in equilibrium. But what happens if we disturb the object from that position? We can see that the weight is going to miss the pivot by that distance d. But that's going to produce a torque that will not return it to the equilibrium position. It's just going to keep on going over more and more and more. And that's what we call an unstable equilibrium. Now what if I put a pivot right in the middle of this block? The center of mass is at the pivot. That would be true in this position, or in this position. It will be in equilibrium no matter how I hold this. We say that's a neutral equilibrium. Looking at the meter stick, the pivot was up above the center of mass, and that's what makes this stable. If I put a weight over to the left, the center of mass is shifted, and the center of mass will be rotated until it comes back underneath the pivot. And this is why we did not do the lab with the pivot on the bottom of the meter stick. As soon as this thing starts to tip, it's going all the way over. We can have a similar discussion with a block of wood placed on a table. It's in equilibrium, stable or unstable. If I disturb it slightly and let go, it comes back to the equilibrium position. That's because as I tilt it, the center of mass is staying between this pivot point and that pivot point. There's two pivot point possibilities here. And as long as the center of mass is between them, it's going to stay stable. But if I go beyond that, the center of mass, the weight, misses that pivot, it starts to come over and it falls all the way. So we can improve the stability by simply laying it down. Now we have a very wide stance. The center of mass is in the middle, and being very low, we have a very stable situation. This gives rise to the idea of things are more stable with a lower center of gravity or a center of mass. Well, let's say I pull on that block as shown. If the block doesn't slip, the bottom left is the pivot. The weight misses that pivot and wants to bring the block back to its original position. Well, how far would I have to pull that block before it won't come back? I'll pull it far enough it'll fall over. Well, the weight coming down from the center of mass is getting closer to the pivot the further I tilt the block. And you can see, eventually, the weight is going right through the pivot. Any further, it's going all over by itself. I won't have to pull on it. If it's perfectly balanced there, we'd say that's an unstable equilibrium. When we lay the block down, the weight coming from the center of mass misses the pivot by a much greater distance. By having a wider stance and a lower center of gravity, we would have to pull this block at a much steeper angle before it will start to fall over. So we would say this is far more stable than standing it upright. So you've heard people say lower center of mass would make something more stable. And that's true for cars. Okay, don't laugh. That's supposed to be a car coming at you. Imagine how far this car would have to tip before that center of mass ended up outside the tire where the pivot point would be. Now you can compare the car to a truck, and that's the back of the truck hauling a heavy load, which raises the center of mass. With such a high center of mass, it won't have to tip as far before it's going over all the way. Well, this seems to work well for a car and a truck. But what about my bicycle? Believe me, when I'm sitting on that bike, my center of mass is way up here, and the pivot is along the road below me. This is quite unstable. This is why you'll fall over if you stand still on the bicycle. That center of mass starts to come over, it's going all the way. You don't have any wide stance to work with. So you need to be moving forward so you can keep steering the bicycle underneath that center of mass.